Okay, so hello everybody. Thank you for coming to the last class of this academic year in the training program. Of course, this is a 5-year program, and so we've just done 3 years now. So there will be something that resumes sometime in late August or in September. But this is the last class before a long break for the summer. Okay, so thank you all as always for being here. What I want to do today is finish up what we were talking about with complex numbers yesterday and show how complex numbers are related to trigonometry, and then we'll have a little closing at the end. So before that, just remember to write your name. I mean, I guess at this point it doesn't matter so much, but it's nice to have a record of attendance. It won't matter because there's no data distribution for next week, but if you'd like to write your name in the chat just for the record, you can do that. Okay, so thank you all for coming. Okay, so I want to start going back over these mechanics that we did with complex numbers, right? So we showed last time how to do addition and multiplication and subtraction and division with complex numbers. And addition and subtraction were very straightforward. And then multiplication was a little less straightforward than that. And then division was a little bit less straightforward than that. So we're going to go over those operations today, and then I'm going to talk about the links to trigonometry, and then I'll try to just say some small amount about why complex numbers, what are their applications. I won't get very deep into that, but I'll mention a couple of their applications. Okay, so so let's do the first problem. Okay, several people submitted answers to this, and the answers were generally correct. So simplify this expression over here: 3 times 2 minus 4i plus 1 plus 6i. Okay, does anybody want to try this one?
Yeah.
Yes.
Right.
Abraham?
Yeah. So first we say three bracket open, and the inner bracket we try to deal with it. So the 3 bracket open. 2 minus 4i.
Yep.
And we say don't bring down the other set, that is plus 1 plus 6i. Now we say, we say 1 plus 2 give us 3.
Right.
3 plus 2i.
Right. So the 1 and the 2 give us 3, and then, right, plus 2i because the 4i and the 6i give us 2i because it's a little cluttered here, but it's minus 4i and then plus 6i. Okay.
Yeah.
Great.
So now so 3 times 3 give us 9. Plus 3 times 2i give us 6i.
Great. All right. Perfect. Okay, that's great. 9 plus 6i. Exactly right. Okay, fantastic. Any questions about this?
Yeah, sure.
Yes, Prince.
Do we have another method to solve this? Let's say, for instance, multiplying the 3 by 2 by 4 and then getting given number. Can it work out that way?
Yeah, sure. So if you want to multiply in the 3 first, that's fine. So you could do first the 3 times 2 minus 4i. So that would give us 6 minus 12i, and then plus the 3 times 1 plus 6i. So that would give 3 plus 18i, right? This would be taking the 3 and multiplying it here first and here. That would give us 6 plus 12i plus 3 plus 18i. And then if you simplify this out, you again would get 9 plus 6i. So yeah, so this way works also, and you get the same answer. Okay, good. Other questions? Yes, James.
Yeah, I'm confused about the problem is getting the 3 is affecting the first parenthesis that you have a resistance between it. between the two parentheses. So that TDS affecting the next parenthesis.
Sorry, can you say that again? I'm not getting you that clearly.
Okay.
Sorry, there's this background noise. I'm not getting you so clear. Yes?
You getting me?
I'm getting you now. Yes.
Yeah, I'm saying like you having three parentheses, the TDS affecting the first parenthesis when operating inside between the first and the second parenthesis. So that's into the affecting the next parenthesis.
Yeah, well, you can't really do this, right? Because look at these this parenthesis goes with this one at the very end, right? So I can't move the 3 inside one parentheses because then it would be getting multiplied by the 2 minus 4i, but not by the 1 plus 6i. So in order to have the 3 really needs to be outside here so that it multiplies both terms. And if I move the 3 inside one of them, then that's going to remove the 3 from multiplying the 1 plus 6i. So that's why I can't just move it in 1. Does that answer the question? I mean, what I'm really doing here with Prince's idea is I'm writing this as, 3 times 2 plus 4i plus 3 times 1 plus 6i. We want a first step. This is the first step over there. Okay, good. Other questions?
Yeah, we're on a stop.
Sorry. Okay. Okay. Let's go to the next one. Okay, so problem 2, evaluate 3 plus 2i divided by 2 plus 3i. We want to simplify it so that it looks like a plus bi, where a and b are real numbers. Let me just write this again, and I'll do it larger. Okay, so what should we do here? How do we simplify this?
Yes, sir.
Yeah, Prince?
The question we look at this fraction, we rationalize the denominator.
Okay, so what do we multiply by?
Yeah, so, yeah, 3 plus 5. Yes. So we have 2 plus 3r or 2 plus 3r.
Right, well, remember, we got to do the opposite. So we have to do the conjugate. It needs to be 2 minus 3i.
Yeah, okay.
Right. Minus 3i, right. Okay.
Yeah.
Okay.
And we cross multiply.
Well, we don't cross multiply, right? We just do a standard multiplying, right?
Yes.
Right.
Okay.
Okay. And so, yeah, so now we have to simplify both the numerator and the denominator here. So what do we get when doing this simplification? So what do we get in the numerator?
Can we guess what?
Yeah.
Is it okay? So we say 3 times 2.
Yep.
3 times 2.
3
6.
times 2. Good. Yes, that's the 3 times 2.
Minus 9.
Minus 9i, right?
9i, yeah.
Yep.
Plus 4i. Minus 6i squared.
Great. And then in the denominator?
4.
Yeah.
Minus 6i. Plus 6i. Minus 9i squared.
Great. Okay, and so now we can simplify this a little bit more. So what is the numerator? Well, this, of course, in the denominator, the minus 6i and the plus 6i cancel each other out. So what does this leave us with?
So we got 6.
Yeah. So 6. Yep.
Minus 5i.
Right.
Minus 6. I square is equal to -1.
Exactly. Right. So this is going to be minus 6 times minus 1, right? This I squared, this is the same as, you know, minus 6 times minus 1 or plus 6, right? So that's good. Okay. And so, and in the denominator, we have the same thing here, right? This is going to be minus 9 times minus 1, right? Sorry, it's a lot of background. Yeah. So for minus 9 times minus 1, right? Great. And so this is just 6 minus 5i plus 6 divided by 4 plus 9. So, great. And if you want to really write it in the form, the point is the denominator is real. So you can now split this up. You get 12 over 13 plus 5 over 13 times I. So if you want this in the final, of writing it. Yes.
Yeah. No concern.
Yes. Question.
Yes,
Yeah.
Princeton,
yes.
Yes, look at the problem there. You get 6 minus 5i plus 6 over 4 plus 9. Now, look at the answer you get. You change the minus to plus in which way?
Sorry. Oh, yeah. Sorry. That's a mistake. Thank you for the fix. That is, this should be a minus. Sorry, minus. That is a mistake. Thank you for the correction. Okay. Yeah, thank you.
Okay.
Yeah. Notice, by the way, you'll see this, the 12 and the 5 and the 13 here. This kind of reminds you of a right triangle. That's actually not a coincidence. Maybe by the end of today's class, I'll be able to explain why you get the 3 sides of a right triangle coming up here, right? 5, 12, 13 makes a right triangle, satisfies the Pythagorean theorem, and that's not a coincidence. It turns out whenever you have something of this form, so like a minus bi, or sorry, excuse me, anytime you have like a plus bi divided by b plus ai, you know, so we're dividing two things where just the coefficients are switched, it turns out that your final answer will always give you things that give you a Pythagorean triple. Okay, so maybe I'll be able to explain that after we finish everything. But like as another example, if you want to do this on your own, you could try, you know, what happens if you do 1 plus 2i divided by 2 plus 1i, 2 plus I, you know, you'll see what this is. I don't remember exactly what the answer is right offhand, but it will also give you something where the denominator looks like a hypotenuse and these two numbers here look like the legs. I think it might give you the 3, 4, 5 right triangle in this case. So worth, you know, maybe let's just do this out just to see it. I'll just do it quickly. So that's 1 plus 2i over 2 plus I times 2 minus I over 2 minus I. This is 1 plus 2i, 2 minus I over 2 plus I, 2 minus I. And if you do this all out, this ends up becoming 3 plus 4i minus I, and then plus 2. Okay, 3 plus 4i minus I plus 2, and then this, I think, oh no, sorry, 2 plus 4i minus I plus 2. And then in the denominator here, we end up getting 4 plus 1, and this simplifies to 4 minus 3i divided by 5. And you see, again, we have the same right triangle of 3, 4, and a 5 here. So it's not a coincidence that this kind of thing will always happen. So maybe I can talk about it a little bit at the end. James, do you have a question? I see your hand raised. Yes. Hello, James. Yep.
How do we derive to get the whole, or let's say the division being whatever about 2 minus 3r over 2 minus 3r?
So this we talked about last week. The point is, when you want to try to divide two complex numbers, what you have to do is multiply by the conjugate of the denominator divided by itself. This is just like rationalizing the denominator when you're trying to simplify a radical expression. I mean, I really is a radical expression. It's the square root of -1, right? So you do the same technique. You multiply by the conjugate over the conjugate. This is just 1. So that's fine to multiply by because you're just multiplying by 1. And when you do that, you're guaranteed that when you simplify everything in the denominator, you're going to get a real number. You're going to get rid of all of the i's in the denominator. These I terms here will always cancel out. So you end up not getting an I in the denominator. And as a result, you just get 12 minus 5i here divided by this real number 13. And that allows you to write the form that you need. Okay, so this is always how you do division. You always find the conjugate, which is the same real part, but the negative of the imaginary part. And you multiply by that in both the numerator and the denominator. And that will guarantee that you can simplify it. Okay. All right. Any other questions on this?
I think it's okay. That
all right. Good. Okay, so let's move on then. I don't know why you're not getting any sound. I think everybody else is getting sound, so you may need to check your phone. I think the sound is fine on our end. Okay, problem 3. Calculate I raised to the 402nd power. So clearly we don't want to just multiply I by itself 402 times. So what's a shortcut that we can use using the laws of exponents in order to simplify this expression?
Yes.
Princeton, yeah.
Yes, we have a appropriate number for complex number that is 4. We can use 4 to divide.
Right.
Yeah. Then.
So, and what's special about 4? So I to the 4 is equal to what?
It's equal to 1.
1, exactly,
Yeah,
right? Because I to the 4 equals I squared times I squared, which is -1 times -1, which is 1, right? Great. So I to the 4 is equal to 1. So now that we know that, what can we do?
So we divide the 4, I raised to 4 and second by 4, which will give you 100.5 by taking the 0.5 and then the 4.
Yeah. Right. So what this means really is 100 with remainder 2.
Yeah, hello?
Yes, hello, Emmanuel.
Can we say because the exponent is an even number, and when you are dividing, hello?
Yes, hello?
You say the number is what raised to what power? I'm not getting it too clear.
So, well, we're doing I is raised to the 402.
Okay, so I was saying if 402, you are looking at the law of exponent, 402 is an even number. I don't know whether you could take it from that angle.
You can. Let's do that afterward. So you can use that, but let's do it afterward. Okay.
Okay.
So this is 100 remainder 2. So what Princeton says, right? Another way you can write this is that 402 is equal to 4 times 100 plus 2. Right. Okay, so that's great. So what do we do with this?
Yeah.
Right. Continue.
Yeah. Yeah, since the remainder is 2, so now we take in I to the 2 power.
Right. So let's write it in a little bit more detail. So what I can say is this is I to the 4 times 100 plus 2, right? Which is equal to I to the 4th to the 100 times I squared, right? I'm using the laws of exponents to do this, right? It's I to the 4 times 100 is I to the 4 to the 100, and then I to the 2 is I to the 2. And because there's a plus here, you have to multiply the two terms, right? And so, I mean, what you're doing is essentially you're doing all this in your head. I to the 4 is just 1, as we've seen, times I squared. And 1 to the 100 is just 1. So Abraham, right? So that's I squared, and I squared is just...
-1.
Exactly. Great. Okay, so I to the 402, if you first look at it, it might look somewhat complicated, but actually it's just negative. Okay, just -1. And right, so because basically when you're raising I to various exponents, only the remainder mod 4, really, only the remainder when you divide by 4 really matters, because every time you raise it to the 4, you're just multiplying by 1. And so that doesn't do anything. Okay. All right, any questions on this? And then I mean, so Emmanuel, I'll show your method also. If you want to use the fact that it's even, you could say that I to the 402 is equal to I to the 201 times I to the 201. I mean, that's okay. But then you just need to do the same thing. And what's I to the 201? This is equal to I to the 200 plus 1, which is I to the 4 to the 50 times I to the 1. And that's just equal to I to the 1, which is just I. And then same thing here, right? You have the same thing here, I to the 200 plus 1, which is I to the 4 to the 50 times I to the 1, which is I to the 1, which is I. And so in the end, you get that you're multiplying these together. So you get I times I, which by definition is -1. Okay, so if you want to use the fact that 402 is even so that you could break it up into two parts, that's okay also. I don't think it's necessarily any easier here because you're basically just have to do the same thing twice over here, whereas for this method, you only have to do it once, but it certainly works. Okay, it's completely fine. Okay, any further questions about this?
Yeah. I have a question.
Yeah, Prince.
Thank you. Actually, I'm confused a bit about where we have R raised to the fourth power, where Princeton may mention about, and then simplifying this equation. Question may arise, where do you get the R raised to the fourth power from?
So where do you get the what from?
Yeah, let me come in there.
Yeah. Okay.
So looking at complex number, it will tell you that the appropriate number to be divided when using the power is 4, because when you square R and R, it will give you +1. So the number to be used is what? 4. So 4 is a correct even number to divide any number raised to, or any complex number that raised to any number. You use what? 4 to be divided.
Yeah, so you always want to divide by 4 because I to the 4th, 4 is the smallest number that gives you 1 when you're raising I to a certain power. So no matter what big number you have here, you know that I to the 4 is 1. So every 4th power you can ignore. And so what really only will end up mattering is the remainder when you divide by 4 in the exponent. Okay?
Okay, so so in case in the other way again, it was not even number, it was not an even number. So were you going to take the remainder under consideration if for any reason it was 401 or 403?
Yeah, exactly. Always the remainder when you divide by 4. So here was 201, and we again have the remainder when you divide by 4, which is 1 in this case. So you always, no matter what it is, even number, odd number, anything, you always take the remainder when you divide by 4.
So then why if I decided I add to the 8th power? I will still go down to the simple.
That's great. So then I to the 8th power, let's write this up here. Right, so I to the 8th power is just, there's no remainder at all, right? It's just I to the 4 squared. And so that's just 1 squared, and that's just going to be 1. So I to the 4 is 1, I to the 8 is 1, and I to any multiple of 4 will always be 1. Yeah, so you're still doing remainder. The remainder is just 0 in this case. So you end up with only a 1.
Over.
Yes, sorry, Hamilton had his hand raised first. Question from Hamilton?
Yeah, so in this case, we are teaching our student one of the shortcut that we were teaching. I don't know whether it's possible, because most of the time the international exam will be multiple choice, right?
Okay. Yeah.
So any other number they give, let's say even they give 600, we know that 400, 4 can go into the 600. So the only portion that we'll be having time for is the remainder.
Yeah.
Then that portion, we just calculate that, and you can do it in even less than 10 seconds. You find the answer.
Yeah, so exactly right. If you're trying to do this for time on a multiple choice exam, so I'm explaining it here because I feel like even if you're explaining a shortcut to your student, it's good to know why the shortcut works in case your students ask more questions. But for a student who needs to do this on a timed multiple choice exam, then yeah, exactly all that you're looking for is what is the remainder when you divide by 4. And you just keep the remainder and you throw out everything else. And that's definitely the fastest way to do everything. You just keep the remainder, and if the remainder is 0, it's 1. If the remainder is 1, you get I. If the remainder is 2, you get -1. And if the remainder is 3, you get -I, right? So I can do this all, so here we have, if this is the remainder, and this is the results. Sorry, over here, if the remainder is 0, 1, 2, or 3, the result, you'll get 1I, -1, or -I. Yes, a question?
No, for me, not question. I want to clear something.
Abraham, yeah.
Yeah. When you look at the I pattern, it will tell you that I raised to the 0 power is equal to 1.
Yep.
I raised to the 1 power is equal to I. I raised to the 2 power is equal to -1. And I raised to the 3 power is equal to -I.
Correct.
So for each time you do your division, you divide by 4. If the remainder is 0, that is, you are getting 1. If the remainder is 1, you get I. If the remainder is 2, you have -1. And if the remainder is 3, you have -I.
Exactly. Yeah, that's exactly how this table works. Okay, great. Thank you. Yes, James?
Yeah, so it's probably come like I raised to the 402 power plus I raised to the 402 power. And let's say if you give your answer not in the I form, what would be the answer? Like,
well, I raised to the 402 power is -1, always. Right, so the answer is -1. That's what I boxed here.
Okay.
Right, answer is -1. That's why I put it in the box. But I mean, the point is that I to the 402 is just the same as I squared. And that's the same as -1, because I is defined to be the square root of -1. So when you square it, you get -1. Okay. All right, other questions?
Yeah. Let me ask this question.
Yeah.
Why in case if we have I raised to 402 power all over I raised to, let's say example now, I raised to 100 power. So in that division sign, what can we do?
Right. So then you can use the laws of exponents, right? So if you had like I to the 402 divided by I to the 100, well, there's a few things you could do. One, you could just use the law of exponents and write this as I to the 402 minus 100, which is I to the 302. And then you could just do this problem. And in fact, you're going to have the same thing that's going to happen here. You're still going to have the, remainder 2. And so in this case, you're just going to get that this is just I squared, which is -1. Or you could just realize that I to the 100 here is just equal to 1, right? Because it's a multiple of 4. So this would just be I to the 402 divided by 1. And we already know the top is -1. So you just get -1 over 1, which is also -1. Right. So you have a couple of things you can do. But the point is that the laws of exponents still work with complex numbers. So if you're dividing this, you can simplify it the same way you would do any other division with exponents. You can always just subtract the exponents to simplify and then evaluate your new thing. That's probably the easiest way to do it. I think this is what I would recommend.
Okay, thank you.
Okay, you're welcome. Other questions? All right, so let's move on. Let's do something a little bit new. So let's recall that we talked about seeing the complex numbers in a plane the last time, right? We had this real axis and we have the imaginary axis. And if I took some complex number, I can look at the point AB. This corresponds to the complex number A plus BI, right? So we view a complex number instead of a real number, which we view on a number line, a complex number we view in a number plane. We view it in the what's called the complex plane. Okay, so this is our point AB, and it's A plus BI. Okay, and so every point, and remember last time I labeled, so the origin corresponds to 0, that's 0 plus 0i. Everything on this axis corresponds to real numbers because the I coefficient is 0. So on the real axis, you get just real numbers. And on the imaginary axis, you get what are called purely imaginary numbers. So that's just some multiple of I. It doesn't have a real part, right? And in general, right, the A here is equal to the real part, and the B here is the imaginary part. Okay. So I want to relate this to trigonometry. Well, why am I doing complex numbers at the end? It's because we've spent a few months studying trigonometry, and I want to show, you know, what are some of these other things that trigonometry can do. So let me draw this same picture again. So let's say I still have my complex number A comma B, which is the same thing as A plus BI. And now, instead of just specifying my number as A plus BI, I can try to specify it in terms of two other quantities. So first, so let me, with a complex number, we usually call it Z. So I'm going to call it Z over here. Okay, so the first thing that I want to specify is that my complex number, I can think of it as lying a certain distance from the origin. Okay, and so this distance from the origin, we call it the absolute value of Z. So if you have a complex number, you can take its absolute value, okay? And that's going to be the length of this line segment from the origin to the complex number. If you think about this, this is the same definition as absolute value for real numbers. You know, what's the absolute value of a real number? It's its distance from 0, right? If I have the real number 3, it's 3 away from 0. If I have the real number minus 3, it's also 3 away from 0, right? So for real numbers, you can think of absolute value as being the distance from 0. And if you think of it with that definition, then the definition with complex numbers is exactly the same. The absolute value is the distance from 0. And using the distance formula, what is this square root of Z? It's exactly the square root of A squared plus B squared, right? This is how we figure out the distance here in the plane. It's the square root of A squared plus B squared. Okay. So that's great. Okay. So now there's a second thing, which is called the argument, and that's the counterclockwise angle from the positive real axis. So if I look at this angle theta here, that angle is called the argument. Okay, so here we would write that theta is equal to arg of Z. Okay, and we generally write this argument in radians. We always do this in radians. Okay, so let me draw a right triangle here. So I can draw a right triangle here, right? And I can label the sides of my right triangle here are A and B, right? Just want to see what's on the next slide. No, okay, yeah. So A and B are the sides of my right triangle, and now I have some relations, right? I have that, for instance, sine of theta is equal to B over the absolute value of Z, and cosine of theta is equal to A over the absolute value of Z, right? So we have that. Or another way of saying it is that A is equal to the absolute value of Z times cosine theta, and B is equal to the absolute value of Z times sine theta. Okay. Okay, where theta is just, I'm using it as shorthand for argument of Z. Okay, so this happens because this is a right-angled triangle, right? So I can use right-angled trigonometry for this. Okay. So this is how it is. And so in particular, if I know what theta is and I know what the absolute value of Z is, then I can determine A and B, right? So if I want to look at the complex number, 3 plus 2i or something, 3 plus 2i, I can look at its absolute value, and I can also look at its argument. And in particular, also, how do I get the argument? Well, let me write this over here. So I also have that tangent of theta is equal to b over a. So if I want to know what theta is, I can use the inverse trig functions, which we spend time talking about, and that's going to tell us that theta is the inverse tangent of b over a. Okay. So let me sum this up on another page. I'll draw this diagram again, just so that I have enough space to write it. But let me just draw this diagram one more time. So this is AB. So this has length A, this has length B. This is my angle theta. And here we have that Z is equal to A plus BI. And this side of the triangle is the absolute value of Z. So what do we have as formulas? Well, in one direction, you have that A is equal to the absolute value of Z cosine theta, and B is equal to the absolute value of Z sine theta. This is just what I wrote. And in the other direction, you have that the absolute value of Z is equal to square root of A squared plus B squared, and you have that theta is equal to the inverse tangent of B over A. Okay, so this shows that if you know the absolute value of Z and you know theta, then you can determine A and B. And likewise, if you know A and B, then you can determine the absolute value of Z and you can determine theta, right? So for example, let's say that I had like 3 plus 3i. If Z is equal to 3 plus 3i, then I can figure out the absolute value of Z is going to be square root of 3 squared plus 3 squared, which is the square root of 18, which is 3 times square root of 2. And then the argument of Z, or what we've been calling theta, is going to be inverse tangent of 3 over 3. And well, that's the same thing as the inverse tangent of 1. And if you want to recall what angle has tangent equal to 1, that angle is pi over 4. Okay, there are 45 degrees. So this becomes pi over 4. Okay, so we can figure out one from the other. Okay. So if you have a complex number, you can figure out its absolute value and its argument. And if you have the absolute value and the argument, you can figure out the complex number, right? I mean, what am I looking for? A, if I take 3 square root of 2 times cosine of pi over 4, right? That's this formula up here, right? This here is absolute value of Z, and this here is theta. Then what do I get? That's going to be 3 square root of 2 times square root of 2 over 2, which is equal to 3 times 2 over 2, which is equal to 3, right? And that's exactly what we want, right? It should be equal to 3 because our number is 3 plus 3i. So this is our way to recover A, to recover the real part. And similarly, if we have 3 square root of 2 times sine of pi over 4, here, this is again the Z absolute value. This is the theta. This is again going to be 3 square root of 2 times square root of 2 over 2. And that's for the same reason going to also be 3. Okay. So the moral of the story is from the standard form, or what's usually called the rectangular form, from A and B, we can determine the absolute value and we can determine theta. And then we can also go backward. If we know the absolute value and we know theta, then we can determine A and B, right? So here we end up recovering A and recovering B. Okay. Okay, so it's just this other form of expressing a complex number. Okay, so questions on this? we're going to show how we use this, but before, just questions on what's going on here?
Hello, sir.
Hello, yes?
Yeah, I have a question. I have a question related to theta is equal to tangent inverse of 3 over 3. And we're having the power here is 3 root 2.
Right. Right. I mean, yeah. So, well, but it's totally different, right? The 3 root 2 has nothing to do with the tangent. The tangent is just pi over, the inverse tangent's pi over 4. Sorry, you're not coming through. I'm not getting you. Sorry, I'm not getting you. Okay, sorry, no, I'm not getting you at all. I think there's something wrong with the network. Oh, there we go.
The answer from the root of 18 is equal to 3 root 2. It's equal to the inverse of tangent
of 1. Right, inverse tangent of 1, which is pi over 4. Yeah. Okay.
Hello, sir.
Okay, good.
But you getting me now, right?
Now I'm getting you, yeah.
Okay.
Okay.
We
So,
have root 18.
yeah.
Well, we have root 18, and then we got the answer to be 3 root 2.
Right, okay.
Exactly.
I mean, the point was I didn't want to spend a lot of time on this. I mean, the 3 is square root of 9, but I just pulled it out. Yeah.
Yeah, but J is where my concern is, June. Well, we have theta is equal to tangent inverse of 3 over 3. How did we get it 3 over 3?
Right. Well, theta, the formula is tangent inverse of b over a, right?
Yes.
So our number is 3 plus 3i, right? The real part is the a, and the imaginary part's the b. So it's just 3 over 3. Right? It's just from this formula. Theta equals inverse tangent of b over a. So the b is the 3 and the a is the 3. Right, so if b over a is 3 over 3. Okay.
All right. It's I've seen it. Okay.
Okay, good. All right, so let me say a little bit more about this. So why would we do this? Well, you know, adding and subtracting complex numbers is pretty easy, but multiplying them is a little bit of a pain. It turns out that multiplication does very well for complex numbers in polar form. So let me just recall this, and then we'll see how it works on the next page. So I'm just going to recall what we had on the previous page. You know, if z equals a plus bi is a complex number, then, right, a is equal to the absolute value of z times cosine of theta, and b is equal to the absolute value of z times sine theta, where here theta is equal to the argument of z. And what that means is that you can write z is equal to, well, a, absolute value of z cosine theta. This is a. And then plus absolute value of z sine theta times I, right? This here is your b. And if you want to simplify this a little bit, you can write this as absolute value of z. You can pull that out times cosine theta plus I sine theta. And here, as always, theta is the argument of z. Okay? So if I want to write a complex number, I can write it as its absolute value times cosine of its argument plus I sine of its argument. And this form here for writing a complex number is called polar form. So in our example, let me just leave a little more space for this. So here, theta is equal to argz. So in our example, we had 3 plus 3i. We could write this as its absolute value, which was 3 times square root of 2, times cosine of pi over 4 plus I sine of pi over 4. Right, this is the example that we did on the previous page. Okay, so this would be, so 3 plus 3i is what would be called the rectangular form. And 3 root 2 times cos pi over 4 plus I sine pi over 4, this is what would be called the polar form. Okay. All right, so we have this rectangular and polar form of a complex number, and they're both the same number. It's just two different ways of writing down what the number is. Okay. So, okay. So let me show why is this useful. Well, let's say we want to multiply complex numbers in polar form. So let's say that we have two complex numbers, and we're going to call them Z1 and Z2. And Z1 I can write as absolute value of Z1 times cosine theta 1, I sine theta 1. And Z2 is the absolute value of Z2 times cosine theta 2 plus I sine theta 2. Right, so here theta 1 is just equal to the argument of Z1, and theta 2 is equal to the argument of Z2. Okay, so now what happens if I multiply them? So how can I write Z1, Z2 in polar form? Well, if I multiply these numbers, what do I get? I get that Z1, Z2 equals, well, the absolute value of Z1 times the absolute value of Z2. These are just real numbers. And then times cosine theta 1 plus I sine theta 1. So I sine theta 1 times cosine theta 2 plus I sine theta 2. Right? This is what happens if I multiply it all together. Now, these absolute values here, these are just real numbers, right? So I can just multiply the absolute values. That's fine. So this is equal to, still just the absolute value of Z1, absolute value of Z2. Now, let me write out this entire product, right? So what do I get here? I get cosine theta 1, cosine theta 2. I think I'll need a little more space. Then plus cosine theta 1 times I sine theta 2. Then plus I sine theta 1 cosine theta 2. And then plus I squared sine theta 1 sine theta 2. This is what I get if I multiply everything out. Just standard, like a quadratic equation, right? Standard FOIL for multiplying out two binomials. So let me simplify this. So this is Z1, Z2. Then here, let me do the real parts first. So I have cosine theta 1, cosine theta 2. And here I have the plus I squared. But remember, this I squared is the same thing as minus 1. So I get cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. And then here I have two things that both have an I. So I'll pull out an I. So plus I times cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. Okay. And now we need to remember, so is everybody okay so far up to this point? What happens when I multiply these two things together? Okay, so
Yes, we are following.
okay, good. Okay, so let's keep going. So now we have to remember our trigonometric formulas. Remember, what's cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2? This turns out to just be cosine of theta 1 plus theta 2, right? This is one of these trig identities that we had. And similarly, we have cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. This turns out to just be I times sine of theta 1 plus theta 2, right? Okay. Okay. So this is a very nice form, right? So this whole thing here is just sine theta 1 plus sine of theta 2. So let me just summarize this. So summary, so what happens? Well, when we multiply two complex numbers, what do we have to do with it? Well, this is the product, right? So it looks like the absolute values multiply and the arguments add. So the absolute values multiply and the arguments add. Yes, question. Right, because the z's, these absolute values, we multiply them by each other. The angles add to each other. Hey, please don't unmute yourself unless you're asking a question or answering a question. Okay, so what this tells us is that polar is a very nice way to multiply two complex numbers, okay? Because it's very straightforward what happens. So just like when you add two complex numbers, the real parts add and the imaginary parts add. Well, when you multiply two complex numbers, well, in rectangular form, it's hard to summarize what happens. You just have to do it out. But in polar form, it's very easy. The absolute values multiply and the arguments add, okay? So this is, right, so over here, right, the new argument, right, the new, or maybe I won't say new, but what this tells us is that the argument of z1, z2 is just equal to theta 1 plus theta 2. Okay, you just add the angles. Okay. So let me,
question.
Yes, question, yes, Prince.
To the first side of this, we'll have cos theta, cos theta 2, minus sin theta 1, sin theta 2. I got, where you got the cos parenthesis will be theta 1 plus theta 2. I understood this point. When I get to the second side of this of this equation right here, where you get plus r sin parenthesis will be theta 1 plus theta 2. From this parenthesis, how do you derive this to get to this point?
So just how do you go from this expression here to sine of theta 1 plus theta 2? To go from here to here?
Yeah, for cosine theta 1, yeah, I got the one clearly. But the second one.
Okay, I mean, this is just the identity for sine. So if you look back and look at the identity of sine of a plus b, it's, cosine a sine b plus sine a cosine b. So it's just the identity that we did about a month ago it's the addition formula for sine.
Okay, but I thought you were just got it from this parenthesis here. I thought you were got it from cos theta, sin theta 2 plus sin theta 1. I thought you were got it from that.
Oh yeah, so sorry, this is not a comma. This is theta 1. This is theta 1.
Oh, okay,
yeah.
theta 1. Okay. So I thought this
there's no commas. It's all theta 1s. Yeah.
Okay.
Okay, so this is just the addition formula for cosine, and this is just the addition formula for sine.
All right.
Okay, so you gotta go look back at the notes from about a month ago, but we derived all of these formulas. Yeah.
Okay.
Okay, great. Okay. So all right. So there we are. Okay, so this is great. So we have this very simple thing. So let's try an application of this. So we multiply two complex numbers. What happens is that the absolute values multiply and the arguments add. And let me say a special case. If we square a complex number, so that's multiplying it by itself, well, then the absolute value squares and the argument doubles, right? Because it gets added, the absolute value gets multiplied by itself, but the argument gets added to itself. So the absolute value squares and the argument doubles. Okay, so here's a question. So this will be the last question we really do. So what is the square root of I? right? So we already talked about powers of I, and we talked how I is the square root of -1, but now I want to know what is the square root of I. So the way we want to do this is like, so how do we do square root of I? Well, what you need to do is write I in polar form. Okay? And so usually you can just see this directly just from the equation, right? I corresponds to the point 0, 1, right? And so the angle from the positive x-axis, this theta, is just going to be 90 degrees, right? It's pi over 2, right? And certainly, so if this 0, 1 here corresponds to I, then what we have is that the absolute value of I is the square root of 0 squared plus 1 squared. That's just 1. And the argument of I, you can see from the picture, is just going to be pi over 2. Okay, so the argument of I is pi over 2. Okay, so you can write I being equal to 1 times cosine pi over 2 plus I sine pi over 2. It looks more complicated, but this is okay. This would be the polar form. So now, how do you take square root? Well, you want something that when you square it, you get I. So you need something whose absolute value is 1, right? Because it has to square to 1, and whose argument is, well, you know, the argument will double when you square it. When you square it, you want to get I. You want to get something whose argument is pi over 2. So if you're doing the square root, squaring doubles the argument. That means taking the square root has to have the argument. So you're looking for something whose argument is pi over 4. Okay, so you need something whose absolute value is 1 and whose argument is pi over 4. Because when you square it, the absolute value will still be 1, but the argument will now be pi over 2. Okay, that's what happens when you square. You double the argument, and that's exactly, if you have something whose absolute value is 1 and whose argument is pi over 2, that number is I, right? This is exactly the number whose absolute value is 1 and whose argument is pi over 2. So what we want is 1 times cosine of pi over 4 plus I sine of pi over 4. Okay, and what is this? Let's just write it out. Well, 1 is just 1. We can ignore it. Cosine of pi over 4 is square root of 2 over 2. And sine of pi over 4 is also square root of 2 over 2. So this turns out to be our number. Okay, so this is equal to the square root of I. Right, and we can test this. You can check. And I'll leave this as an exercise, but check that square root of 2 over 2 plus I square root of 2 over 2. Check that if you take this and you square it, you actually get I. Okay, so it's a square root, because if you square it, you get I. Okay, so one of the nice things about polar form is this might be hard to solve for in general. If I just was trying to find a complex number whose square was I, in rectangular form, that's not at all clear how you would do that. But in polar form, it's much easier because you just need to find something whose argument is half the thing that you're taking the square root of. So the absolute value needs to be the square root of the absolute value you want, and the argument needs to be half of the argument that you want. So square root of 1 is just 1, and half of pi over 2 is pi over 4. Okay, and so then you write this down with argument pi over 4 and absolute value 1. Use this polar form. And once you have that, then when you square it, it turns out that you exactly get I. So this is an exercise to just check this, just multiply it out, do this times itself. You know how to multiply two complex numbers. So you'll multiply it out. You're going to find it's going to simplify down to I. Okay? And so what this shows us, remember I mentioned this fundamental theorem of algebra last time, but this shows us that we don't need to invent new numbers to do things like taking the square root of I, right? Remember, I was this new number that we had to invent in order to take the square root of -1. But in order to do the square root of I, we don't need anything new. We just have another complex number. This is still a complex number. It's not a new kind of number. Okay, once you have I, you may as well have numbers like this also. So we don't have to pass to some kind of new number system in order to take the square root of I. Okay, we can just solve for it. Okay, it's just an equation that we can solve. And this fundamental theorem of algebra that we talked about last time says actually you can solve any equation once you're in the complex numbers. You never have to leave it. Okay. All right. So so that's that. And so maybe the last time okay, so the last time is sorry, so the last thing I want to say is that why do we study these complex numbers? So there's a lot of reasons, but the main applications are in anything that has to do with waves and electrical engineering. So it turns out that complex numbers are very, very useful for telling you about the equations that model alternating current. So when you have current, you have two different kinds. There's direct current and there's alternating current. It turns out that alternating current, when you write down the equations for, what the voltage is like at any given time, or, what the current flow is at any given time, that these are very naturally modeled by complex numbers. If you want to do sound engineering, picking out, you have some sound waves and you want to amplify certain parts of them and minimize other parts, it turns out that this relies on Fourier analysis, which is really reliant on complex numbers. And then I should say that if you're interested in physics and you eventually study quantum mechanics, that basically all of the equations for quantum mechanics are stated in terms of complex numbers also. Okay, so these complex things are not just, we use the word imaginary, but they're not just some imaginary thing that we make up in order to ask math questions. They really are the natural setting for a lot of very important science, in particular, a lot of electrical engineering and a lot of quantum mechanics really rely on these complex numbers. Okay. Okay, so any questions about this example or about any of that? Yep. Mm-hmm.
The root of 2 plus r, the root of 2 over 2 square gives you r.
Mm-hmm.
That's why that's it exposing it out to say that multiplying the root of 2 over 2 plus r, the root of 2 over 2. I'm not saying.
Okay, let's do it. We've got a little time. Let's do it. Okay, so square root of 2 over 2 plus square root of 2 over 2i times square root of 2 over 2 plus square root of 2 over 2i. Okay, we're squaring it, so we multiply it by itself. So what do we get? We get square root of 2 over 2 times square root of 2 over 2 plus square root of 2 over 2 times square root of 2 over 2i, and then plus square root of 2 over 2 square root of 2 over 2i, and then plus square root of 2 over 2 square root of 2 over 2i squared. Right? This is what happens when you take all four terms, right? The first term is these, then for the i's you get the middle two terms, and then the outer two terms, and then lastly you get these. Now square root of 2 over 2 times square root of 2 over 2 is just 2 over 4. That's just 1/2, right? So this is just 1/2 plus 1/2 I plus 1/2 I plus 1/2 I squared. But I squared is -1, right? So this is 1/2 plus 1/2 I plus 1/2 I minus 1/2, right? Because this I squared here, remember, is equal to -1. And now we see what happens, right? The -1/2 and the +1/2 cancels, and we add 1/2 I and 1/2 I, and we end up with I. So it just comes out to I. But why were we guaranteed that this was going to work? It's because we did this argument with the trig, with the sine and cosine addition formulas. That's how we knew to try this number. Otherwise, who would ever guess that this is the square root of I, right? It's not the kind of thing that you would guess. The only reason you can come up with it is by using this polar form and knowing that what you really want to do is have the angle involved in the argument. Okay. Does that clarify a little?
It's okay. It's okay. I understand it.
Good. Okay, so let me move to the end. So that's basically the end. So I think this is a nice example to close on, and it really brings together a lot of the trigonometry we've been doing to show you how it relates to complex numbers, how you can do everything with complex numbers. So I want to to give some thank yous during our closing. So I want to acknowledge, first of all of the teachers, all of the participants for coming week after week, all the time, and giving me your attention for all of this time. So thank you for your attention for a great year. I definitely want to thank Sange and Charles and Abraham for taking, a huge amount of effort to organize this, to distribute the data, to recruit teachers, do everything else. And I should thank, of course, Asimana, Mr. Randolph, who's here. I should thank him also just for always inspiring me. And whenever I have questions about how the program is going, I call him up and we talk, and he always gives me great advice. So I want to do a very special thank you for Mr. Randolph. Of course, none of this would be happening without him. Just there's no way I could do this program by myself. So thank you to everybody who's helped organize it. And if I'm forgetting some people, I apologize, but I'd like to, acknowledge everybody who's contributed to the success of this program, and that includes all of the participants also. So also just in terms of institutions, we definitely get support from the Liberian Ministry of Education. The funds for this come from the National Science Foundation of the United States, so always want to acknowledge them here. I'm supported by my own university, by Baruch College, City University of New York. And in terms of recruiting participants, I always want to thank the I Help Liberia project, who is, really organizing everything here, both in the United States and in Liberia. So some notes about certification. So certificates will be given to everybody who participated substantially in the program. So you're not going to get a certificate if you just showed up one time. But if you came a substantial number of times, then you will get a certificate. So the general rules will be, if you attended a significant number of classes, you'll get a certificate of participation. If you attended almost all of the classes, maybe the data wasn't good one time or you were traveling, that's okay. Then you'll receive a certificate of completion, and then certificates of distinction will be given to those who not only attended almost all of the classes, but who also significantly enhanced the class through their active participation and or effort on homework problems. So there will be a few certificates of distinction. I'm going to announce the lists of people for each certification next week. So I'll send a chat on the WhatsApp with the list of participation and the list of completion and the list of distinction. So I'll send that out next week. In the meantime, please just write the WhatsApp chat just so that I have your name with the correct spelling, because I want to make sure that everything is written correctly for the certificates. I guess let me just show, I haven't made the certificates yet because I need to know who they're going to be signed by. So I need to make them, but I'll just show you quickly what last year's looked like. So let me get this up. All right, let's see, here we are. So what do the certificates look like last time? What is this? Oh, I don't want that. Oh, did it just open a PowerPoint? No. Sorry, let me, here we are. Okay, so let me do, okay, so this is, let me share. So this is, basically what the certificates looked like last time. I don't know, I have to figure out who they're going to be signed by at the ministry this year. But this is basically what they're going to look like, but it'll be a certificate of whatever you have and your name and the correct year. And I have to talk to Sange to figure out who the certificate will be signed by. So this is one from last year's session. And then I'm going to print these all out in the US, and somebody will go to Liberia at some point, and I'm going to have them bring the certificates with me, with them. And hopefully there should be some kind of ceremony in Monrovia and in Ganta where you can come and receive your certificates sometime later in the summer. Okay. So I'll hopefully get those done in the next week or two, and then we'll figure out the next person who's coming to Liberia and can bring them. So let me just reshare my screen. Here. No, what did I do? Okay, here we are. All right, good. Okay, but yeah, in the meantime, at some point this week, make sure you send me your name with the correct spelling so that I don't make any mistakes on the certificates. And as always, I'm going to send out a survey where you can give feedback about what improvements you would like to be made to the program next year. Are there topics that you think should be covered? Any feedback, any suggestions, the comments that you have about the program, I want to hear from them because I'm going to spend the summer thinking of ways to improve the program. So I appreciate you if you can participate in that survey. So I'll send that out to the group probably some point next week. And just want to thank everybody again for all of your participation and attention this year. I had a really good time, and I hope we all learned some serious math. So thank you again. And I guess I should say if Sange or Mr. Randolph wish to say anything, please do.
Yes, thank you so much. Hello.
Hello. Yeah.
Yeah. Thank you so much, Andrew, for everything, for the training and all the time funds put into this program. And also my appreciation will go to Mr. Randa and the IHEL Liberia team for their continuous support to our program in Liberia. We so appreciate everything. I will discuss, you have a new administration, and then AB is supposed to be meeting with my new boss. And then I will get to him and get back to you who will be signing the certificate.
Okay, good. Yeah, so I want to make sure that I get their name correct and certainly their spelling correct as well.
Okay.
Okay, great, thanks.
Thank you so much.
You're welcome. Mr. Randolph, do you want to say hi?
Yeah.
Okay.
Are you hearing me?
Yes, but we're seeing your neck.
Yes, we are here.
Okay. Are you, Dr. Ubbers, thanks. And we appreciate what you have done for us. And we wish you the best for the summer. And please come back. And please come back to give us some more of your insight in mathematics. But also, I'm asking you give a presentation this week at another program. Can you make that available to us?
Oh, yes.
Yeah.
Well, actually, I only have the recording for my second talk. So the first talk, Mr. Kona made the recording, and he has it. And
Okay.
so I don't have the link to it. I only have the recording for my second talk.
Yeah, because I attended the first, and the first was is also related to math research, and it would be good if we listen to it as a group also.
Okay. So what I can do, I can send the slides for both talks.
Yes.
And I can send the recording for the second talk.
Okay. Okay.
Yeah, the first recording I don't have. But if we ask Mr. Kona, maybe he has it and he can send it.
Yes. And another interesting development that I like from that talk was that the full participation from those from the north, southeast.
Mm-hmm.
The southeasterners were involved in the talk,
mm-hmm.
and from the University of Maryland. And so, can we engage them so that we can extend what we are doing now in math at this level. That would be interesting. And engaging the new administration would be of interest also. I teachers, I'm very sorry I have not been participating or hearing you, but today I decided to sacrifice the time to come in and listen. And Dr. Overs, you are welcome to not only teach math, but you are welcome to travel back to Liberia and visit us. I think Sanjay, Madam Sanjay would like to see you and your family. Not only you, but bring the entire family with you. Liberia is safe to accommodate you.
Well,
Thank you.
Thank you very much. Thank you for the invitation. William Boandolo, you have your hand raised.
Hello?
Hello, yep.
This is Emmanuel from Maryland. Yeah, I've been having a little challenge on my internet today, but at least I didn't get a piece where our dear brother was talking about the university in Maryland. I don't know whether America, Maryland, or the Liberia, Maryland.
No, Liberia.
Okay. I'm from Tottenham University, the math department at the College of Education. And I think most of those topics I went through, I listened to them very keenly, and they are part of our curriculum. Yeah, so that's very well. Thank you. So I hope you extend the program at Tottenham University in Maryland County, the land of sunshine.
Okay, you're welcome. Thank you. Yeah, no, we definitely meant Liberia, Maryland. There were people from Tubman University. I think they're on Wednesday. William, do you have your hand raised? Okay, no, you're muted. Yeah, I think you need to turn your sound on.
Yeah. What I'm saying, I'm from there. You getting me?
Yeah.
Yeah, I say I'm from.
Sorry, no, not getting you anymore.
Yes, sir.
Yeah. Yes, Prince.
Just appreciation to you for the level of time you have been giving us. Actually, saying I started with this program, and I have enjoyed, and I'm still enjoying this program. This is my third year on this program.
University.
So I really appreciate.
Sorry, one person at a time, please.
Yeah, that all right.
Yes. Abraham?
Yeah. I want to appreciate you and the organizer of this program. And this program is very helpful to we, the math teachers in Liberia. It helps us a lot because looking at the curriculum, when some of us look at the curriculum, some topic there that we not really have control of, we bypass it. And that also harm the learner. So I think with this topic, with this program, we are able to, go in detail with the curriculum. So I want to appreciate you and the organizer for this program. Thank you very much.
All right, you're welcome. Harrison?
Hello, sir.
Yes, hello? Yes.
Prince, getting me now,
yes,
right?
Prince again, yes. Okay. Yeah, getting you.
Yes, sir. I just appreciate you for this program. This program has been good since I started this my third year, and I've been enjoying this program. Actually, it helps me a lot, give me wide knowledge, make me to research more on some topics what I never even did in high school. And then from this program, at least I was successful, and then to capture myself into it. And then I do appreciate every other effort from you and also from Mother Sangye. She did well at times,
She will make it possible to do our data distribution whatsoever. No matter what happens, she will have lesser time. She will do it as much as possible, for us to be in class. So I just want to appreciate all of you. Thanks so much. And we pray that we'll continue this program on a good atmosphere as we go on.
All right. Thank you. Harrison?
Yes. How you doing?
Good. How are you?
I'm doing good. I'm very grateful. This is my first time to participate in this program, and it has been an amazing journey from day one to today. I'm very grateful and I appreciate you and the organizing team on ground that is in Liberia. And I also want to say, let God bless you, your family, your university, and all of the program that you are running. Let it continue to impact life. You will continue to be remembered in society. Thank you very much. Liberian, I appreciate you. This program is making a great impact on our educational setup. I salute you. Thank you very much.
All right, you're welcome. Thank you for participating. William, did you want to say something? I see you have your hand up, but it's yeah, there we are. Okay, good.
Getting me now?
Yeah, getting you now.
Oh, okay. So I want to highly appreciate you for the level of education imparted onto us for now. I think it is my second semester, or maybe my second time with this program. The first time I started, I thought it was just a mere program, but with kind of level of time I have spent, I think you have increased my knowledge from square one to at least to square two. There are some topics that some of us I know have over at time in the class, but from this program, I can boldly do some activities when I'm actually teaching now with a practical example. Not just teaching now like or in a classroom teacher, but teaching as a practical teacher. I highly appreciate you. And the strong one go to our mother Songate. She's always willing. I can actually give her a hard time to be real. Some day the day she saw that way, she forget to send me cut. I was saying a lot of communication, but at least she one person that willing at any time to respond to people communication, so she will respond to you. If she's not actually online, as soon as she gets back online, she sees your communication, she'll respond to you. I just want to appreciate mother. Thumbs up for you. I appreciate you. And I hope this program will continue so that our knowledge can continue to increase. And as our knowledge increase, we also impart it onto other children that are coming out. Thanks. I do appreciate.
All right, you're welcome. Marcus?
Yeah, so let me say once again, thank you so much. For me, I've seen you in person. I think you came in Liberia before, and I reached out, I was staying in Liberia as well. And then this is my third time because I graduated from the Lakota teaching college in 2022. And since we started this program, I think I just continue to be my mathematical thinking, just continue to increase on a daily basis. Given the university I'm attending, majority of what we are doing, like especially the statistics, because nothing about the accounting department whatsoever we do, everything, every process you are do, you have to do it contains mathematics. Yeah, so I really want to appreciate you. This is my third time, even though I'm not in Liberia, but the second time I didn't. I got my certificate from you, but you say it's not signed. And Sati called me and said you still have my second certificate. So is any way possible you can still give my third certificate to
I'll get both. Yeah, I'll get both.
Yeah.
Those who didn't receive their certificate will have it here. I will check if it is there. Then anytime you get the means to get it, we can do it.
Mother Sange, let me say, man, thank you so much, Mother. Thank you so much. You very good at communication. I don't know what I did mass communication. You're very good. You respond to every message. Anytime I send you message, you come in and reply. That shows that you are a mother and you know how to work with people. Thank you so much, and thank you so much, Dada Andrew, for the knowledge. I really appreciate.
Thank you too.
All right, you're welcome. By the way, I'm just going to end